afternoon, everyone, and welcome to the session, Tool Shop Optimization, Concurrent Engineering for today's mold shop. Presenting for us today is David Lindeman, Senior Applications Engineer for Cimatron Technologies. For those of you who are not familiar with Cimatron, you can see on this slide a few fast facts. With more than 20,000 installations worldwide, Cimatron is a leading provider of integrated CAD/CAM solutions for mold, tool, and die makers, as well as manufacturers of discrete parts. Our business is to help you succeed, and that is why we are hosting our presentation today. Before we get into the actual demonstration, I have just a couple of logistics to cover. First, how to submit questions. We, of course, encourage your questions, and Dave will answer as many questions as he can during the Q&A session at the end of the presentation. So, as questions occur to you, please send a note to Lisa Sterling, moderator, which you can select from the drop-down menu. To do this, click on the Send Note button in your upper left-hand corner of your screen, type in your question, and click Send. There's no need to wait until the end of the presentation to begin submitting questions. In fact, we prefer you submit them as they occur to you so that we can better prepare for the Q&A session. If we do not have time to cover your questions, we will be sure to contact you one-on-one after the session. We also recommend that you click the Enlarge button to view the full presentation on your full screen. You'll want to select With Toolbar so that you can keep your Send Note button handy for submitting questions. And with that, I would like to turn the floor over to Dave to begin the demonstration.
Thank you very much, Lisa. Appreciate that. As you know, our subject today is concurrent engineering, and particularly how it applies to mold shop. So what we'll be discussing is what exactly concurrent engineering is, and importantly, what it is not, so that we understand clearly how it is best used. We're finding concurrent engineering is, in many cases, the key to improving delivery time for many of our customers. So the question is then that we would do well to consider is it something that could work for you? So let's take a look first at what we see as the typical process taking place within a mold shop. And from there we'll build upon that. Of course, data is read in and it's evaluated when a job is received. From there it's usually decided who is best suited to do the design work, or it's given to the next available designer to begin the job. There's always a series of reviews, design reviews that take place as everyone decides if that's the exact design they want to go with. Usually at this place too, steel can be ordered and the job is considered released onto manufacturing. From there it's like throwing it over the wall in a sense. As the design is done, it's now thrown over to the shop floor, where it's up to them now to take the data and to proceed on with the actual making of the mold. And with this slide we can see some of the typical tasks that involves. Of course, doing EDM work, making the electrodes and then burning them in position on the cavities, or it could be some CNC milling to take place on the cavity parting lines. Mold is made up of a lot of small components, so drilling must take place. Waterlines are a particular feature of that, and then it all has to be put together. So all these different operations we find too could even be their own independent department. Now each one of these involves different types of machines, obviously, but the data that is sent to those machines or the people doing these processes often is different types of data. Wiring in could get 2D data. The guys doing the plate drilling could get a blueprint. The NC cavity guys that are doing the 3-axis milling could get a 3D surface. So this is all different forms of data now that are being propagated throughout the mold making process. So it raises the question, if you had to find where the information actually was, could you do it? Where is all the information that's used to generate this job? It may seem like an overly simple question. It may seem at times even to be irrelevant. Yet when we think about where things are going and how the data is organized and how are things centrally located, it does raise some interesting scenarios. For instance, the quote itself that first started all this may still be sitting on the salesman's laptop. Decisions were made back then that affect the outcome of the job. They may be printed out in an Excel spreadsheet, stuffed in a folder, stuffed in a file cabinet somewhere. The actual design itself, which is typically the one thing that is kept from job to job, is probably still sitting somewhere on a CAD server, whereas the NC code, the floor that probably been thrown away already. And finally a drawing, if it still exists, probably rolled up in a corner somewhere covered with grease and dust, or it's been stuffed away in a file cabinet. With different types of data going in different directions, of course the question is it all the same? Does it actually all get the right information so that the mold comes together correctly? It's scattered. And again, the question is, could you retrieve it? And that becomes relevant when we start talking about engineering changes. Because if the data is already gone, or if we're considered irrelevant, we haven't kept it, then we can't update it. So we're actually going back through the process in many cases. We're regenerating the G-code, and we're regenerating the path around the wire EDM machine, which creates a difficulty of making sure that every department is actually up to speed with the right engineering level. A simple thing like not printing out a blueprint could be something costly in the end that could result in making mistakes. Now that was a kind of a quick rundown of what we see in a lot of shops. We want to now explore this a little deeper. We're going to introduce you to a shop that we looked at and spent some time with, and we got to know their process quite well and had some suggestions for them. And you might find this interesting yourself if you even see some of the things that mirror your own process as we go through this. Looking back in the design department, we found they had different design softwares. Over the years, they had collected different design softwares with each individual that they hired. So one guy was good at one type of design software, another guy knew nothing of the first design, he had his own software. So when a job was released, it would be given to whoever was first available as a designer who was open to take the job. He would then read it into his software he's most familiar with, even though the evaluation was perhaps done on something entirely different when the manager made that decision. So right away we have a situation involving multiple translations before the job has even begun. Once the design was accomplished, it's then, of course, sent over the wall onto the NC department, where, again, a translation takes place into the NC softwares. In the particular case with this customer, that was entirely dependent upon the machine that they were going to use to manufacture it. So they had different softwares for different machines. It also resulted in a backlog on some machines, as you're dealing now with the question of are those softwares as efficient as one another. One may be better suited to the type of cutting than another, and that one's creating a backlog. Also, it deals with how efficient the individual who programs it is with that particular software. Why did all this happen? Why are they running this way? Well, it's because they've relied on an evolved process. As the business grows, you add more functionality and capabilities to the shop, and things just kind of grow up in that way. For instance, they buy a new machine. Of course, they want to get the most out of that new machine, make it as effective as they can. So usually they buy a new software with it. Usually that software could have been recommended by the machine vendor, telling you that this is how they're going to get the most efficiency by programming it in this particular software. Or they hired a new designer, and that designer, well qualified as a mold designer, didn't happen to know the design software that they had on at the time. So it's that he could be effective immediately on hire. They go out and they buy a seat of the software he knows. So now multiple softwares are accruing within the design department. What we see oftentimes, as was the case with this particular shop, they want to expand their capabilities. They want to be able to go into new markets and show that they have new technologies that will help them to do a better job and be quicker at making a mold. For instance, they may go deeper into EDM software for a machine that has 2D orbiting or 3D orbiting. Well, now they're looking again at looking slag on a print? Does the print match the data that's going to be used to cut this new engineering change, or cut the electrode that's going to make this engineering change? So what was really happening to them? Well, they found that with this, just by sitting down and taking a look at what they were doing, they were repeating the same processes again and again, really starting over many of the manufacturing processes in the shop. Of course, that means losing money. And in this particular case, because the original quote was soft just to get the job, they were losing money on the engineering changes that were hoped for so that they could get that money back. And that, of course, means the whole job was a loss to them. And to make matters worse, not only did they not make money, but they were late on the delivery. And as you know, when an engineering change comes in, often the customer still wants that part in the original time frame. Now, it's to make the money, you have to provide it within that original time frame. Those are the constraints we work within in the mold industry, and sadly, that's the kind of thing that can happen. Well, then what is concurrent engineering, and how is it going to help the typical mold shop, or the mold shop, we might say, in the situation of this one particular customer? We want to understand what it isn't as well as what it is. We're not talking about just being able to respond to the urgency of the situation. Something has come up, there's a change, and now we're all scrambling to make the due date, like an all hands on deck kind of thinking. A person may feel, well, I'm devoting more of my shop resources to getting the job done. I must be doing concurrent engineering. Really, that's not the case. We'll look at other things too that a mold shop will do, like perhaps having a designer work overtime so that he can get the design through quicker, get the job done quicker. Maybe they're going to commit more NC machines to cutting the components that are going to go into this mold. Maybe even incorporate a second shift to compress the time frame of putting it together. Then there's the ugly word called outsourcing, where finally admit defeat that you're not going to make the delivery time, or your machines are at capacity. So now you have to go to another company to have them cut the job for you, which means you're sharing profit with them that you did not intend to share. So in all, though, when we look at these, which you might call quick fixes, we're still dealing with the issue of throwing the data over the wall. It's the process itself that actually has not changed. We have to wait for the design to be done before the NC can continue. So that means increasing the cost of the finished job. Okay. So what is concurrent engineering? Well, for one thing, it's not crisis management. It's not the design system for jumping in when things have gone bad, but actually the system is designed at the very beginning to avoid the crisis. It means a design workflow where all phases of the manufacturing can look in on the concurrent process and they will all remain current. It means being able to take an engineering change and adapting to it on the fly and still keep all your processes current. It means working smarter, not working harder, or working in a panic. What do we need if we're going to bring in this concurrent engineering? Well, it requires the right mindset. It means looking at things differently. That may mean we have to take an open-minded look at our current process or our particular part of it that we're responsible for. How often do we translate the data is the first thing we may look at. That tells us something about the process. As we look at the process, can we identify what's holding up the flow? Are the designs getting through as quickly as we'd like? Am I getting a backlog in my EDM department? And all those questions point to yet another question. The softwares I'm using, do they allow for it, or are they actually hindering it? Are they creating the situation that we're dealing with? So with a new mindset comes training. It's time to train people on the new process and develop new patterns of thinking and also new skills required in order to use concurrent engineering. So let's talk about concurrent engineering and a good example of it. And we're actually going to start at the very, very beginning with the quote. And that's because we find here's the first time that data is actually handled and that decisions are made that affect the job. We're finding in most mold shops it requires many quotes just to get a single job. And decisions are made in the quote phase that could affect the entire job. A good quoter will look at the tip positions and look to find slide actions, undercuts, or lifters. He'll consider if this is a hot runner job, on and on the many decisions that are required that affect the cost of the job. And the question is now, if those decisions made, are they documented well enough that that information could actually be passed on to the design department at kickoff, thereby giving the design that much more of a head start. Looking in on design then, in a concurrent engineering situation, the design is not a one-man-does-it-all necessarily type of process, but could actually have multiple design processes going on at the same time. An example might be one designer working on the cavity side details while another is working on the core side. It could be, like you see outlined here, one designer may be working on something like sleeve ejection while another is working on the other side of the tool putting in the manifold or the hot runner system. In some cases it could be different processes going on, not just different design parts. So for instance, one designer might still be putting in the water lines while the design's going on, yet that could possibly not hold up another designer from pulling the electrodes and getting that process started. That's the idea of concurrent engineering, is that more than one task itself is being accomplished, as opposed to waiting for one to finish all before another can begin. And also, it would involve quickly taking an engineering change on the fly at whatever stage the design is at, and then updating the design so that that engineering change will be passed on throughout the whole system. From there, we'll throw in the NC and assembly departments. Immediately, it means that both those departments can see on their screens that the data they're looking at has changed. So it's not like they're informed by getting an email or someone runs down the hallway and yells at the department to hold the job up because there's an engineering change coming. When they bring up their data, they see it, and the system tells them things have changed. Same thing when it comes to looking on the assembly department. With a shop floor viewing capability to look in on the design, they would see immediately, again, the design has changed and the notification in the bill of materials that parts have changed. With all this taking place, again, the NC department now has the option of not just reprogramming it, but actually allowing it to recalculate if they haven't started cutting the steel yet before the change was incorporated. Really, do they need to reprogram it? I mean, do they know the tool they're going to rough with? Do they know the step overs? Do they know the feed rates? Well, most of the time the step's going to stay the same. So now it's a matter of recalculating as opposed to going through the thought processes of reprogramming. Well, how do we do this? It sounds well enough, but what's required to do it? Clearly by now, by the things we described, it means incorporating one system that's actually designed with concurrent engineering in mind from the start. And with that one system, it means that system has to understand your work, it has to understand your shop and what you do. For instance, you're always going to be dealing with the material, the plastic material itself. The part will have to be put into the correct position or tip position. You'll have to deal with expansion for the shrinkage conditions. This system should be able to know the decisions you've made and then incorporate that with every engineering change. Otherwise, you're left behind with what you call a paper trail, your own roadmap of notes that you wrote down, reminding you of the exact shrinkage you used, where you rotated the part about, and what angle you tipped it at. And very often, the job folder will have this setup sheet for the designer who has to follow up with the engineering change so that he knows what the first designer did. The system is smart enough to know that and save that and thereby eliminate the possible mistakes that could occur right at the beginning of the engineering change. Likewise, the type of mold pieces that you use can be standardized within the software as well as the particular components that you use. Not all molds are the same. Some shops will spend most of their time building DME type mold bases that they can order, while other shops will never do that, but they custom build each one of their molds from scratch. Well, there's different requirements for larger molds than there are the smaller molds, different types of components. That information can be saved and then used again and again in a wizard interface that will allow the standards to be kept right within the software. Now you know we can see the holes, since we know that drilling and pocketing is such a major part of making a mold, a function that will actually see those holes and then apply the processes to the holes that we use. For instance, you know the tools you're going to use when you use a 1/4-20 tap. You know you're going to spot drill. You know the diameter of the drill you're going to use. You know the tap. Save the information in the system. The system learns how you do it, and now it sees that hole the next time it does processes to it. That's the automation we're talking about. Then if there's a change, the system can update, knowing how you're going to go about cutting the hole anyway. We also apply that thinking then when it comes to our 3-axis milling. How often are the strategies the same when you rough a job or when you semi-finish a job? Very often. So use that again and again, and if the data were to change, then the template would still apply, or that process would still apply. Likewise, assembly understands a design change. For instance, this person who's putting the assembly together may be relying on a blueprint, or in this case, looking at the computer itself where a print is stored and saved. That print will update with new views and also a live bill of materials that updates showing what new components are being used. So many shops are using shop floor viewers instead of relying on paper anymore because they want to be able to have instant access like this. And that's something well worth thinking about when it comes especially to concurrent engineering. So let's take a closer look at the software. Now, as you know, I work for Cimatron. The purpose of this presentation, though, isn't to give you a product demo. We're more than happy to show you the software in that fashion, should that be something that you want to look at. We wanted to stay on subject, though, and talk about concurrent engineering, if nothing about in terms of your own process. So while I'm showing you glimpses of the software itself, we want to stay on topic of concurrent engineering. For instance, here you're looking at how the software interacts with the data received so that I understand the part. I'm quickly getting the overall volume. I'm looking down and seeing and finding resistance to clamp. All that information that I'm going to need to know when I start laying out the overall steel sizes for this part. It also, this is a situation where I would put in the shrinkage so that that information stays with the job throughout the length of the job. Perhaps it's an unpleasant question to ask, but have you ever had a job go through that wasn't expanded or that was double expanded? So many places I myself have worked with and have to deal with that. But not having it in the software where it is accessible and will be used is one of the situations that can create that. Setting up the tip is one of the biggest features of getting a job right. And so often, the tip is dictated by the part itself. There'll be features on this part that you have to look at in order to get your die draw correct. Here you're looking at a picture where there's a lot of red marks showing there's a backdraft undercut condition. Well, basically, I'm looking at this tip right now in the wrong direction, so I'm trapping it. And you can see the diagram that shows you the color scheme, which, of course, this is customizable. If it's red, true verticals being in that grayish blue, and if it's flat, it'll come out in the green color. The system will allow you to interrogate the information, the data itself, find the feature that you feel most likely will create the best tip condition, and here we reprocess or recalculate so the system shows us what is the tip. So maybe I'm off like 5 degrees in order to rock that thing around in its correct position. Compound tipping is very common where you have to go 2 axes to get the right tip. That is saved right now in the system. It knows that axis of motion and will allow me to design based upon that being tip position. So very easy to keep track of what is car body position, original design position, what is mold position and its correct tip, and where I have expanded it from. The system knows all that. Going a little further with this, that being said, there being actions involved inside the part itself, here you see a lifter and a slide condition. It's good to know if you can actually pull that out in the correct position. If you look at the lower left, you see the red sitting on that little slide. Well, based upon the way it was designed, that area would be undercut on that slide. So I have decisions to make. Do I redesign it? Do I make suggestions to the customer telling them we can't pull that out unless we create that part differently? Here you've got a database that allows you to communicate it and store those changes throughout. less than 1/8 of an inch in red, and that gives me a real good indication of areas where I'm going to be putting in an electrode. Let the system do the work for you. Likewise, here the decisions are being made about setting up the splits. You see the side actions for the cavity, the core, and also the lifter and the slide. All that is stored within the database and will be used later on down the road. So decisions are being made here, whether it be in the quote or maybe the designer is doing this work right now. But the important thing is it's being saved. It's going to be used later on down the road in future processes. For instance, I've got the direction of motion for that slide. That tells me how the mechanism needs to be set up. So use that motion when the mechanism is being designed. Things like that lend themselves to concurrent engineering. We talked about engineering changes, and to show you that this is integrated into the system, here you see engineering change that's been caught by the system. It basically compares the old and the new data and colors it up so that you can see it. Then you have some choices. Do I automatically bring that new data into my existing working part file, or do I try to work with it independently on its own? If I bring it right into the part with the new data, that immediately updates all my drawings and it flags everybody and then sees that the data's changed. From there, I may make a few decisions. Does it affect parting line? Do I need to move an ejector pin? Do I need to move a water line? While you're seeing the change here just on the part itself, this system allows you to make the change and view it in the tool so that you can see how the cavity is going to change. Do you have to go and weld it now? Or does this require an additional NC operation to clear out a bigger plastic area? All that allows for the quick decisions that can be updated immediately, then everybody knows what's going on. Now we're talking a little further about engineering changes in NC as we get down the road, so keep that thought in mind. With that comes understanding what your shop is doing, especially in your mold bases. We talked about having standards built right into the system that know how you like to make your molds. For instance, here you're looking at one of the pages in the mold design package that helps the designer estimate how much steel he wants around his part in the X and Y direction, how much steel he wants backing up the part in the Z direction, what's his minimum ejector stroke. You can put in his offsets or gaps on parting line, or even create an overlap condition if he's going to direct cut the A to B plate. But what's the best size? Well, here, if this is something being done in the quote, you can see just throwing the part in and then quickly getting a mold base around it helps generate the correct size. But it's going to be based on the size standards that you as a shop work with. For instance, again, following the rules we set up, what types of plates do I want? Do I want a manifold plate? Do I want a top clamping plate? All of these can be handled for non-standard idea when we talk about libraries and catalogs. Perhaps you can see in the left side panel some of the different catalogs that are already built into the system. You may have some of your own unique components. A number of our customers do, and some they've made available that we can pass on to other customers. But you have the ability to store your own components with knowledge of the hole it sits in so that you can use this automated function. Likewise, here's the bill of materials. If one click said, show me all the components, show me how many, show me what they're made of. And there's a stock size function that will generate overall sizes for order on my own to make my slides and lifters and things like that, or cavity inserts. Another major process involved in making the tool is the electrode. As you well know, and there are decisions that are made there. Here's just a screenshot to show you an electrode. This is something that many people spend some time looking at inside of Cimatron because it's been automated, where with a single click, areas are defined as burning areas, and then standards are put into place. My holder, the size of graphite that I keep in my tool grip, and the way I want to extend my surface's tangent from the burn area so that I get the type of electrode I want. The burn location is immediately established that way, and it's stored in the system. So now it's not a matter of me walking up to the EDM controller and punching in the numbers. It's late on a Friday and I'm tired, and 3/4 of an inch suddenly becomes 0.57, or I fat finger the number. That's a killer. Right there, where you've got the job nearly done, 90% done, and burning something in the wrong location is one of the most painful things that we hear coming from old shops. That data is retrieved from the system, and then using this system is brought into the EDM controller. So with CNC type of EDM controller, it can be customized whether you're dealing with the Charmy, like there's an example of the Charmy control. So it knows the location, it knows the spark gap values you want to use. If you're using a Charmy, you're looking at the RBF files and how it's going to control the machine. And even if you've taken it to CMM and you've touched off on it to find out if it was cut in exact position or not, those offsets can be programmed, as well as setting up the order. All that can be done. We're finding that that's done oftentimes on a viewer right there on the floor. That way the EDM operator can set up his run order the way he wants it. Going back to that, I jumped ahead, sorry, but perhaps you can see that there's more to it than just pulling a trode in its position and burning it. What about multi-cavity situations? This could go in orders that you prescribe. 1, 2, 3, 4. Take the electrode, if it's a double-sided electrode, rotate it 180 degrees, and then burn backwards 5, 4, 3, 2, 1, that kind of thing. So that kind of customization is built in automatically. Now we talked about the importance of NC always seeing the current design. And it sounds good in theory a lot of times, but practicality, people wonder, well, so what? Here's cutter path, already programmed, you're just reapplying it. That's all you're telling me. There's more to it than that, and I hope that I can illustrate that. Now, you may be in process of building the cavity and then get the engineering order changed. Where is your steel? How much have you cut? Can you actually continue the engineering change with this chunk of steel that you started with, or have you removed too much material? How do you know? What Cimatron does is keep track of the stock. So yes, it's an automation feature that's nice for applying a cutter path to remaining material and not air cutting, or knowing what material is left so that the cutter won't go into an area and snap off because there's too much material. But when we're talking about the concurrent engineering process, it's also very valuable for me to take my engineering change file and look at the remaining material that's sitting on the machine. Now I know if I need to go get another block. Now I know if I can continue with the steel that's already there. It's an important part of the decision that gets ignored because no one knows. You just try it, you drop the cavity, and you put a shim behind it, trying to recover that particular chunk of material. Likewise with the holes. An engineering change doesn't just change the date of the part, as you know, but it may require, well, if that ejector pin moves, how many holes have I drilled? And have I already drilled a hole in its wrong location? Do I need to go back and re-drill new holes? Well, this will automatically find that because it knows what has been drilled and what hasn't been drilled. And when a new hole occurs, it flags the process so that it can now have the automatic drilling you. We let's do a quick review again of this. We hope that you can see it as something that can increase productivity and shorten delivery time, most of all making your shop more responsive to the ever-growing needs and demands and changes that your customers throw at you, and still keeping your bottom line profitable. So the question is this something for you? Can concurrent engineering be a success at your shop? Okay, now we'd like to look at some questions that you may have submitted, so we're going to be passing the phone back and forth, and I'll bring Lisa back.
Great, thank you so much, David. We will now begin the Q&A session. The first question that came in was, you mentioned you have a mold quote package. What does it include?
The mold quote package allows the quotation guide to view the geometry through cross sections, understand tip positions, see the separations, the splits. You can look at material properties. You can look for the minimum radius conditions, all that kind of information. The idea is to eliminate the CAD functions, so he goes right to those functions that are relevant to him, and he can extract the data he needs, perhaps even throw a mold base around it in some cases, so that he can get the estimation together, get some materials, and get some part definition together. So basically, it's a small version of the software, which is the functionality that he needs.
Okay, great. Next on the list, I have a Makino EDM machine. Does your Electrode Setup work with Makino machines?
Yes, it can. I believe I showed the CimatronE machine earlier. Makino, it's just the same way. We have already customers with Makino machines using EDM setup in this way. It's a matter of understanding your needs for your machine. So it's not like just Makino and CimatronE. We can do this with any EDM machine as long as we can get the data to it. So it does require a certain amount of setup. All right, we may have to do some customization to meet your needs, but that's something that we can look at down the road.
Okay. You say concurrent engineering shortens delivery time. What are typical results that you are seeing?
That honestly can vary, of course. It depends upon the type of jobs involved. Not long ago, the Aberdeen Group Mold and Die Shop Benchmark did a study, and they went through some of our customers, Cimatron customers, and compared them to other mold makers. And what they found, let's use an example, when an average tool shop would do, 9.3 weeks would be the length of the job required for them, using systems and the same machines out there that everybody's using. The best that they got out of non-Cimatron users at that time was 8 points, so there's actually quite a bit of variance in that. When they checked Cimatron customers using this concurrent engineering process, they found that Cimatron customers were coming in at 7.9. So that's the best machines, the best, what we say, the best software for every given task, if the Cimatron customers were coming in ahead. So the concurrent engineering process does have quite a bit of validity.
Okay, thanks, Dave. I believe you partially answered this next question with that answer, but do you have any customers using this concurrent engineering process that we could talk with?
Sure, we'd be happy to provide you with list of names, numbers that you can contact.
And we're just about running out of time, so I'll take one more question. Are you expecting your customers to replace all of their existing software at one time?
Ooh, that would be hard, wouldn't it? No. We understand that your shop has to stay active. You still got to get molds out the door. So really, that's not a realistic solution. What we've looked at is an implementation plan that we found very effective in helping to bring a shop up to speed on Cimatron. The goal isn't to take a
time, I would like to conclude our session. We're just about out of time. Thank you all for joining us, and if we happen to not get to